Hi everyone, welcome to NEETshala Organic Chemistry Revision Lecture Series. In this series, we will be covering all the chapters of organic chemistry for NEET examination. So let's get started. Before we begin, do not forget to like, comment your queries, suggestions and doubts below, share it with your friends and also subscribe to NEETshala YouTube channel, and also you could be a part of the Telegram channel for all the updates related to the upcoming videos. So let's start. Today we will be having the part 1 of the organic revision lecture series, wherein we will be covering about alkenes. Now what are alkenes? Alkenes are a class of saturated hydrocarbons. They are a class of saturated hydrocarbons which is having a general formula of CnH2n plus 2. This is the general formula for alkanes, where N is going to be the number of carbon. So let's move on. In this chapter, we will be mainly discussing the structure of methane. Then we will be discussing about the IUPAC nomenclature, isomerism, preparation of alkanes, and the properties of alkanes. So let's discuss about the structure of methane first. Now, if I'm checking the structure of methane, I can understand that it is tetrahedral in structure and it is having a hybridization of sp3. So if it is sp3, we can say that the bond angle between carbon and hydrogen is coming out to be 109.5 degree. Now what is the value of carbon-carbon bond length? If I take higher alkanes, we have carbon-carbon bond length, and that carbon-carbon bond length is coming out to be 154 picometer, and carbon-hydrogen bond length is coming out to be 112 picometer. So that's all about the structure of methane. Now let's move on to the IUPAC nomenclature. So here I have taken the example of C6H14. We are going to construct the isomers of C6H14 and we will name those compounds according to the rules of IUPAC nomenclature. So let's get started. Let's make the isomers one by one. Before that, what are isomers? Isomers are basically the compounds which have the same molecular formula but have the different structures. So if I take C6H14, we can arrange it like this. This is the first possibility. We can arrange 6 carbons in a straight chain, then it is known as normal hexane. Second, we can arrange 5 carbons in a row and we can keep 1 carbon as a substituent. Now that substituent cannot be placed at the first position, because if I place it like this, now this is going to be my longest chain. So that is same as the first one. So we will neglect this chain because we don't want repetitions in isomerism. So we are going to remove it from here and let's add it to the second position. So this is going to be the second compound, that is known as 2-methyl pentane. Now what is the third possibility? Third possibility is we can place it at the third position. Now what are we getting? Now we are getting 3-methyl and the parent hydrocarbon is pentane, so we can name it as 3-methyl pentane. Now we are going to remove one more carbon from the main chain and we are going to add 2 substituents. Again, we cannot add it at this and this position. This is not possible. So we can eliminate that option and we can place it over here and here. So this is another possibility. So we have a methyl group at the second position and also at the third position. So we can say it is 2,3 dimethyl and the parent chain over here is butane. So it is 2,3 dimethyl butane. Now what about the fifth one? Fifth one is where I am going to place both substituents on a single carbon. So that I can place it either here or I can place it on this carbon. Both are the same. So we will get 2,2-dimethyl butane as the next isomer. So these are the different isomers of C6H14. Let us now study the preparation of alkanes. Now we can prepare alkanes from a variety of compounds like alkenes, alkynes, haloalkanes, alcohols, aldehydes, ketones, carboxylic acids, and amines. Now, in this chapter, we will not be discussing about amines because from amines we will be preparing from Grignard's reagent, and Grignard's reagent we will be dealing separately in the chapter haloalkenes and haloarenes. So, let us start with alkenes. Now, if we have to prepare it from unsaturated hydrocarbon, that is alkene or alkyne, then we have to use addition of hydrogen. And addition of hydrogen, as you know, the process is called as hydrogenation. For hydrogenation, we can use a variety of catalysts like platinum, palladium, or nickel. Now, platinum and palladium is usually taken at the room temperature, but nickel is taken at relatively higher temperature and pressure. And if we are using nickel for the process of hydrogenation, then it is known as Sebastian-Sanderson's reaction. Sebastian-Sanderson's reaction. Now, the most important point to note is that platinum, palladium, and nickel should be finely divided. Finely divided so that it has very large surface area for carrying out the reaction. Now, let us see how the reaction is carried out. As you can see over here, we have ethene here, CH2 double bond CH2. We are going to add hydrogen on both sides of the double bond, that is over here and also over here. Now, how is the mechanism? First of all, we have CH2 double bond CH2. This is going to undergo homolytic fission so that both the carbon will get one hydrogen each. So we have CH2 single bond CH2. This carbon is also having a dot, that is, it has one electron, and this also has another electron. Now let us take hydrogen, H2. H2 will also undergo homolytic cleavage and it will form two hydrogen free radical. So one hydrogen free radical will come over here and another hydrogen free radical will come over here. So let us join these two with a single bond, and now what we're getting, this is known as ethane. So we got ethane here, and this is the method of hydrogenation. So what was the mechanism that was followed? The mechanism that was followed is nothing but free radical addition reaction. So let us take propene. We just have to remove the double bond, and to the either sides we have to add hydrogen, so we will get propane. Now what if we are given an alkyne such as propine? So in that particular case we have to do the process of hydrogenation twice. When we are doing the process of hydrogenation one time, we will be getting alkene, and when we are doing it again, we will be getting it as propane. So now let us see a question based on this. So as you can see over here, look at this question. So how to add the CH3? This is a classical example for AIMS level of questions. We have to remember that if we are considering stereochemistry, we have to understand that addition of hydrogen is syn addition. Syn addition का मतलब है कि hydrogen is added to the same side, either towards the observer or away from the observer. Here we can see that the hydrogen is added in such a way that it is facing the observer, and here it is added in such a way that it is moving away from the observer. So these are the two different possibilities in which we can add hydrogen, and we will be getting two different compounds in the ratio 1:1. So that is why it is a free radical addition and also a syn addition if we are considering the stereochemistry. So let us take another example here. So what to do? We have to break this bond and we have to add hydrogen. Now that hydrogen can either be facing towards the observer, or another possibility is it can move away from the observer. Now let us take the second class of compounds, that is alkyl halides. How can we prepare alkanes from alkyl halides? We have two methods. Method number one is reduction. For reduction we will use zinc and dilute hydrochloric acid. So if I am taking CH3Cl plus H2 in the presence of zinc in acidic medium, that is in the presence of dilute HCl, what is going to happen? This hydrogen is going to split to give hydrogen free radical, and one of the free radical is going to react with a chlorine free radical that is generated from this molecule to form HCl, and it is going to the other hydrogen free radical is going to react with the CH3 to form CH4. So we get CH4 and also we get HCl as the product. Now, there is a limitation for this reaction as well. What is that limitation? The following reaction cannot be used for fluorides because of its very high bond dissociation enthalpy. So let's move on to the next compound, next reaction. How can we prepare it from Wood's reaction? Now, what is Wood's reaction? Wood's reaction, what we are going to do is we are going to take two molecules of either the same alkane, so alkyl halide, or we can take two different alkyl halides. So case 1, let us take the same alkyl halides. So let us take CH3Br plus. We need to take a metal, that is sodium. So we will take two molecules of sodium and we will take another molecule of the alkyl halide, that is CH3Br. So we can remove this NaBr like this and we can join this CH3 and CH3. So that is the mechanism. So if we have one carbon over here in the reagents, or we can say in the reactants, if we have one carbon, we will get one alkane which is having double the number of carbon. That is, we will have two carbon. Now if we have two carbon in the reagent, then we will have four in the product. Now if I am taking two different alkenes, alkyl halides, like CH3Br plus 2Na, and this sodium should always be placed in dry ethereal medium. Now why not wet ethereal medium? Because if we are placing it in wet ethereal medium, then it can lead to explosion because sodium is very rapidly reacting with water to form heat. So let us take two different alkyl halides now, CH3Br plus 2Na plus let us take CH3CH2Br. So let us remove the NaBr first of all. Let us remove the NaBr. Now, here we are going to get three major products. How three major products? We have one compound having one carbon. So in the product, we should double the number of carbon. So we will get CH3CH3. Second, we are going to take this compound and we are going to double the number of carbons. So we will get 4 carbon containing butane, CH3CH2, CH2, CH3. And these are the expected products. We have another product that is formed by combining this CH3Br and this CH3CH2Br. We can see that this compound has only one carbon and this compound has only two carbon. So we have to add this 1 and 2. We get 3 carbon containing propane also. So what are the three main products that we get over here? Let us take the general reaction now. Rx plus R dash X plus 2 molecules of sodium in dry ether. In dry ether, it is going to give us RR plus R dash plus RR dash. Now what is the mechanism followed in Wood's reaction? In Wood's reaction, the mechanism followed is going to be again free radical mechanism. Free radical mechanism. Now in this mechanism also, in this process also, there are some unwanted products. Let us see what are those unwanted products. We have a possibility for generation of carbocation. So let us take an example. If I take CH3Br, it is going to form CH3 free radical and also Br free radical. Now if I take CH3 CH2Br, it is going to give us CH3 CH2 free radical. Right now there is another possibility, like we have CH2 and I can write a hydrogen over here, and there is a possibility for cleavage over here, right? So that cleavage will result in a free radical on the carbon, and here already we have a free radical. So this hydrogen is moving out as H plus. Now there is a possibility of forming a double bond between these two. So CH2 double bond CH2 can also be formed, but this is going to be a minor product, right? So alkenes is also formed in Wood's reaction, but as a minor product, and in organic chemistry usually we do not represent these minor products. So let us now look at the next reaction, but before that, let us see some of the related reaction. Like when we learn about Wood's reaction, we are also supposed to learn phytic reaction and Wood's phytic reaction. In Wood's reaction, we have taken alkyl halides, but in phytic reaction, we will take aryl halides, and in Wood's phytic reaction, we will be taking alkyl halide and also aryl halide. So two compounds we will be taking over there. So let's move on to the next one, that is conversion of alcohols to alkanes, aldehydes to alkanes, and also ketones to alkane. For all these three conversions, we can use red phosphorus in the presence of iodine, and this is going to act as the reducing agent. It is a weak reducing agent which can convert alcohols to alkanes, aldehydes to alkanes, and ketones to alkanes. But for these two, we generally use Clemenson's or Wolff-Kishner reduction rather than red phosphorus and iodine. So let us see Clemenson's reduction. In Clemenson's reduction, what is happening? We have an aldehyde or ketone. So the CO group is converted into CH2 group by using the reagent zinc amalgam in the presence of HCl. So we need acidic medium for carrying out Clemenson reduction, and in Wolff-Kishner reduction we are taking a ketone or an aldehyde. We are going to react it with hydrazine in KOH at high temperature. We will be getting alkane. So here also the same bond cleavage is going to happen. CO is going to convert to CH2. So as we can see, there is addition of hydrogen and removal of oxygen. So both of these are going to be reduction reactions. Now, here we can see that Clemenson reduction is active at acidic pH and Wolff-Kishner reduction is active at basic pH. So if we have any like acid sensitive groups like OH will react with H plus, right? So if we have any such acid sensitive groups, then we cannot use Clemenson reduction because it will misguide the reaction and we will get some other product which is not required. So let us see one question related to this. As you can see over here, we need to carry out the following conversion. What is the reagent that is required? So here we have OH. OH, as you know, is an acid sensitive group. Hence, it is going to react with the H plus and it will convert it into water. H plus plus OH minus will form water, right? So this is a mild oxidizing agent, so we cannot use this also, and hence we cannot use this also because it will form some other products, not the desired product. So we have to use only Wolff-Kishner reduction in the presence of acid sensitive group. Now let us see what will happen in this particular question. Here we can see that we have bromine. Here you can see bromine over here, and bromine is not a base sensitive group, but we have an adjacent hydrogen, right? This adjacent hydrogen is an alpha hydrogen, and alpha hydrogen is always an acidic hydrogen. So this acidic hydrogen can react with the OH minus if we are carrying out the Wolff-Kishner reduction, and it can form an alkene, and that is not the desired product, right? So we cannot carry out this particular reaction, that is Wolff-Kishner reduction, when there is compounds containing alpha hydrogen, because alpha hydrogen is an acidic hydrogen and that will misguide the reaction. So this is the limitations of these two reactions, that is Clemenson's reduction and Wolff-Kishner reduction. Now let us move on to the next topic, that is preparation from carboxylic acids. Now if we have to prepare it from carboxylic acids, we can use two methods again. One is known as decarboxylation and another is known as Kolbe's electrolysis. Now what is decarboxylation? For decarboxylation, we can react the acid with NaOH and CaO. The mixture of NaOH and CaO is known as soda lime. It is known as soda lime, and this is taken in the ratio 3:1. 3:1, where 3 parts of sodium hydroxide and 1 part of calcium oxide is taken. Now, when we are reacting, it is decarboxylation. Always remember, D means removal. So, decarboxylation means there is removal of one carbon dioxide, or we can say one carbon molecule, and that is moving out as Na2CO3 over here. Usually, we can take it as one carbon containing compound is moving out. It can be either carbon dioxide or any other compounds like these, Na2CO3. So as a result, if we have 4 carbon, or we can say n carbon in general, if we have n carbons in the reactant side, so n carbon in the reactant side, we will have n minus 1 carbon in the product side. And what will be the reagent? The reagent is going to be an acid, and the product is going to be an alkane. So the process is decarboxylation. Now this type of questions are expected from here. This is an NCERT example. Now what is this question? Sodium salt of which acid will be needed for the preparation of propane? So first of all, we will take an acid and we will react it with NaOH so that we get the sodium salt. Now this sodium salt is treated with the soda lime mixture, and as a result of that, it is eliminating a molecule of Na2CO3 and we will be getting the product. So let us see what is the product that what is the salt that is required over here. So here it is given that the product is propane. So product will have 3 carbon. So how many carbons will be present in the reagent? It will be n plus 1. So that is coming out to be 4. So we have 4 carbon in the reactant side. So since we have 4 carbon in the reactant side, it is going to be butanoic acid. Now let us see the second method, that is known as Kolbe's electrolysis. Now Kolbe's electrolysis is again a free radical mechanism. So let us see how the process is carried out. So here we are going to take an aqueous solution of the sodium or potassium salt of a carboxylic acid, and we are going to carry out its electrolysis. This electrolysis will give rise to an alkane which is containing even number of carbon atoms at the anode. So let us take the process in detail. Suppose I have CH3COONA. This is a sodium salt of a carboxylic acid. This on dissociation will give us CH3COO minus and Na plus. Now this is a cationic species and this is going to be an anionic species. Now if you could remember from the electrochemistry chapter that cationic species will move towards the cathode and will reduce, and the anionic species will move towards the anode and will oxidize. So let us take the cathode reaction. Since we are taking the aqueous solution of the salt, there will be water also, right? So water will also move towards the cathode. So there is H2O giving rise to H plus plus OH minus, and Na plus is going to take up one of the electron to form Na. But remember that there is some OH minus molecules which will react with some of the Na plus molecule also. So a few amount of base is also produced, that is NaOH. NaOH is also produced along with the sodium atoms that is formed. So the solution overall is going to be basic. Now let us see what will happen at the anode. At anode we have CH3COO minus. So this will undergo oxidation. Now we have 2 electron here, right? We have a negative charge, and negative charge means we have 2 electrons. So we are going to convert it into a free radical. So we have CH3 free radical plus there is elimination of CO2 happening over here. So if I take 2 molecules of CH3COO minus, we will get 2 molecules of CH3 free radical and 2 molecules of carbon dioxide. So now these 2 free radicals of CH3 is going to react with each other and is going to form the desired product, that is ethane. So let us see how that happens. We have CH3 free radical reacting with CH3 free radical to form C2H6, right? So this is what is happening in the Kolb's electrolysis. So here we can see at the anode oxidation is happening. So what is happening? Two electrons are being removed. So from two molecules, two electrons are being removed. So the negative charge of the oxygen is converted into free radical. Now there is elimination. So there is cleavage here, and ultimately there is elimination of carbon dioxide. And two molecules of methyl free radicals are reacting to give the desired product. At anode we can see two reactions. One is OH minus formation. Some of the OH minus will react with the Na plus in the solution to form NaOH as well. Now we cannot prepare methane from Kolbe's electrolysis because we do not have any compound which is having any carboxylic acid having less than one carbon, right? We need compounds which is having less than one carbon to prepare methane, and that is not possible. Hence we cannot prepare methane, but we can prepare from ethane onwards, and usually we prepare for even number. Now let us take a flowchart to understand Kolb's electrolysis in a little more elaborate way. If we have a monocarboxylic acid like propanoic acid, we will get alkane on carrying out the Kolb's electrolysis. But if we have a dicarboxylic acid like succinic acid, let us take it out. What is happening when we have succinic acid? So in the case of succinic acid, we have COOH, CH2, CH2, COOH. This is the formula for succinic acid. So the first step is we have to convert the hydrogen into sodium. This is the first step. So we have to remove the hydrogen and we are going to add sodium. Next step, we have to form the ions. So we can remove the sodium and we can add negative charge. Next is oxidation. When we are carrying out oxidation, we are going to remove the COO and we are also going to remove the COO minus. So ultimately, this much part is removed and now we are left with a CH2 free radical, and also we have a CH2 free radical over here. These two free radicals are going to react to form a bond, so we will be getting an alkene. Now let us take another example, that is CH double bond CH double bond CH, single bond COOH, single bond COOH. This is known as fumaric acid. So if I am carrying out the same process for fumaric acid, there is elimination of two molecules of carbon dioxide. Two molecules of carbon dioxide is eliminated because in the first step we are removing the hydrogen. So now there is a free radical formed over here and there also a free radical, so there is a triple bond formation. So from dienoic acid we will be getting an alkyne. So here we will be getting an alkyne if we are using dienoic acid, and if we are using a dicarboxylic acid there will be an alkene. So once again, a quick recap for the trick for Kolb's electrolysis. If we are asked a question from Kolb's electrolysis without doing the mechanism, we can do it directly. Like we have CH3, CH2, COOH. We have to prepare alkane. So what to do? We just have to remove this part. Just form a free radical. Take the another molecule. If that is also same, then let us take it as same. Now join these two with a single bond. These two free radicals are joined with a single bond. Now we get butane. If we took 2 carbon containing molecule in the reagent side, we will be getting 4 carbon containing product side, right? So that is all about the Kolb's electrolysis. So that is the end of preparation of alkenes. So let us just quickly recap the preparation of alkenes. We have discussed the preparation of alkenes from alkenes. From alkenes we can use hydrogenation, that is addition of hydrogen. From alkynes also we can do it the same method. Haloalkanes we can use reduction using zinc and HCl, and another method is Wood's reaction. Wood's reaction, what is the reagent? It is sodium in dry ether. What is happening? If we have CH3Br, that is going to react with another molecule of CH3Br, will form CH3CH3. So general reaction is RR plus 2 molecules of sodium plus R dash X, sorry, Rx plus 2 molecules of sodium plus R dash X will form RR plus R dash plus R dash R. Now, from alcohols we can use red phosphorus in the presence of iodine. From aldehydes and ketones we can use Clemmensen reduction or Wolff-Kishner reduction. From carboxylic acid we can carry out decarboxylation, or we can use Kolb's electrolysis. Now let us see the conformations of alkanes. Here we will be just discussing a brief introduction of conformation. We have a separate video on isomerism wherein we will discuss about this in detail. Now, what is conformations? Conformations means these are the spatial arrangement of carbon atoms. It is the spatial arrangement of carbon atoms which is formed by the rotation of a single carbon-carbon bond. That means if I have a carbon-carbon bond like this is a carbon and this is also a carbon, I'm going to rotate this bond, and the rotation of this bond will result in different structures, or we can say different spatial arrangements. These spatial arrangements are called as conformers or rotamers. Now, what are the two conformers of ethane? For ethane, we have an eclipsed configuration and a staggered configuration. Now we can see over here that the staggered configuration is more stable than the eclipsed configuration. In eclipsed configuration, we have to remember that the dihedral angle, that is the angle of turning, is 0 degree or approximately 0 degree, and in the case of staggered configuration, the angle of turning or the dihedral angle is coming out to be 60 degree approx. Let us move on to the physical properties. In physical properties, first one important is the nature. So as we can see over here, C1 to C4 are gases, C5 to C17 are liquids, and those which are higher than 18 carbons, they are going to be solids. So this state is important. And second important thing is related to their solubility. We know like dissolves in like, so we can say they are soluble in organic solvents. Now, next one is boiling point. So boiling point, we have to remember just 2 points. That is, boiling point depends on the length of the carbon, or we can say number of carbon in the chain. And second factor that is considered is branching. When the number of carbon increases, boiling point also will increase, and when the branching increases, boiling point will decrease. So let us take a table here. As you can see over here, we have butane, 2-methylpropane. These two are having same number of carbons, right? These two are having same number of carbons, but what is happening to the boiling point? Butane is having a higher boiling point than 2-methylpropane. Why? Because branching is present in 2-methylpropane. So always remember, branching will decreases the boiling point and number of carbons will increase the boiling point. So if you are asked to compare the boiling point, first factor that we have to consider is the number of carbon chain, and if the number of carbons in a chain is same, then we have to consider the branching. So now let's move on to the reactions of alkanes. We have the following categories of reactions in alkanes. First one is substitution reaction. Second is oxidation reaction. In oxidation, we have complete, incomplete, and controlled oxidation. In controlled oxidation, we have reaction with copper, reaction with KMnO4, reaction with MO2O3, and also we have reaction with manganese acetate. Then we have isomerization, aromatization, and finally we have pyrolysis. So let us take this one by one. First one is known as substitution reactions. Now what is substitution reactions? Here one or more hydrogen atoms can be replaced by halogens or nitro group or sulfonic acid group. This is known as substitution. Now halogenation can take place at higher temperature, or it can take place in the presence of diffuse sunlight or in the presence of ultraviolet sunlight. Now the lower alkanes are not usually going to undergo nitration and sulfonation reaction. This is also important. So let us take the chlorination here. Now what is chlorination? We are adding chlorine, or we are substituting, we can say, we are substituting chlorine one by one. Here we have a 4 hydrogen, so we are removing one of the hydrogen and we are going to substitute it with a chlorine, so we get CH3Cl. Now if I am adding, or we can say if we are substituting one more molecule of chlorine, we get CH2Cl2. If we are substituting one more chlorine, we get CHCl3, and if we are substituting one more chlorine, we will be getting CCl4. Now let us see the priority orders. Now this is an important concept because if we get a difficult question, this is important. If we have a primary carbon, if we have a primary hydrogen, we can say the hydrogen which is present on a primary carbon is known as primary hydrogen. So the primary hydrogen has a selectivity value of 1 secondary will have a selectivity value of 3.8 and tertiary is having a selectivity value of 5. Now what does this mean? Let us take an example to understand what is the selectivity order and what is the significance of this selectivity order. Why do we need this selectivity order and all? Here we can see a compound. Let us look at this question. Identify the major product when this particular compound is subjected to chlorination. So here what we have to do, we have taken the compound here, and what we are going to do is we are going to categorize the hydrogens as primary, secondary and tertiary. This carbon and this carbon is same. We can say they are equivalent. But this is also a primary carbon, but this is not equivalent to this. So this is a primary hydrogen. So let us put how many similar type of hydrogen are there here? 6. So let us take their priority order or the selectivity order as 6. Now this one has 3 hydrogen of the same type and their overall selectivity order is 3. Here we can see this is secondary. Secondary will have approximately 4 as the selectivity order. So let us have 8 here because we have 2 hydrogen. So the selectivity order is 2 into 4 is equal to 8. Here also we have the selectivity order as 8. This is a tertiary hydrogen, so its selectivity order is coming as 5. So overall we can say that we have different hydrogen and we have assigned these selectivity values for each of these hydrogen. Now, which is having the maximum selectivity value? The maximum selectivity is 8 and that is for a secondary carbon, or we can say secondary hydrogen. So now in this particular molecule, the chlorine will substitute first the secondary carbon, or we can say it will substitute the secondary hydrogen, not the tertiary, not the primary, because chlorine does not have a very specific nature. It can substitute either in the primary or in the secondary or in the tertiary. It depends on the selectivity order, that is 5 is to 3.8 is to 1. Which is greater, it will go and substitute over there. Like it is like a person, if he gets MBBS then also he will study, and if he does not get MBBS then also he will study. That is the nature of chlorine. But if we take the case of bromine, the story is different. In the case of bromine, if he get MBBS then he will study, but if he don't get MBBS he will not study. He is very particular, so he will go and react only if there is a tertiary compound. So there is order tertiary greater than secondary greater than primary. Now fluorination is too violent to be controlled, and iodination is very slow and it is almost a reversible reaction, and hence it is carried out in the presence of oxidizing agents like HiO3 or HNO3, so that we can remove the excess of Hi that is formed, because this Hi is going to convert the reaction in the opposite direction. It is going to carry out the reaction in the opposite direction also, but that is not desirable here, right? So since it is not desirable over here, we are going to restrict that by adding HNO3 or HiO3, which are oxidizing agents. Now the mechanism is very simple. It is a 3-step mechanism. We have initiation, where we have generation of free radicals. Now the free radicals are combining with each other to form different other free radicals. That is known as propagation. Here we can see there is formation of CH3 free radical and Cl free radical, and the final step is known as termination. In termination, two free radicals are going to combine to form a molecule so as to stop the chain growth. So this is known as chain termination reaction. So this is about chlorination. Now let us take the second reaction, that is combustion. Now combustion is basically reaction with oxygen. So when we are reacting a methane or any other hydrocarbon with oxygen, we will be getting carbon dioxide and water. And how to balance this equation? If we learn this equation, it is well and good. We can directly substitute. Otherwise also we can directly balance it by the normal traditional method of balancing, the trial and error method. Now if we are carrying out incomplete combustion, we will not be getting carbon dioxide. We get water, but we will not get carbon dioxide. Instead we get carbon in the solid form. Now this is known as carbon black, and that is used for the manufacture of ink, printer ink, black pigments, and also it can act as filters. Now the third one is controlled oxidation. Controlled oxidation, we have 4 conditions here. First one is by using copper. If we are using copper, we can convert an alkane to an alcohol, corresponding alcohol. Now what is the meaning of corresponding? Corresponding means if we have one carbon in the reactant side, we will have one carbon in the product side. The same number of carbons in the reactant and the product side, that is known as, we can say, corresponding. So here we get corresponding alcohol. Second compound, we have used MO2O3, so that will convert it into so here we have methanol, sorry, we have methanol here, so it is converting it into corresponding aldehyde. Now we have alkane, which is reacting with manganese acetate, so we are getting acid here, carboxylic acid here. Now this is the most important reaction. We have a tertiary alkane that is converted into a tertiary alcohol by using KMnO4, and here we cannot use primary and secondary, we will just use tertiary alkane to convert it into tertiary alcohol. Let us move on to the next reaction, that is isomerization. Isomerization is the production of isomers of a particular compound. We have reagent here, anhydrous AlCl3 and HCl. So if I am treating a particular compound with anhydrous AlCl3 and HCl, we will be getting its corresponding isomers. These two are the major products, and then we have the minor isomers also. Next, aromatization. In aromatization, if we have 6 carbon containing or more than 6 carbon containing compounds, they are heated at 773 Kelvin and 10 to 20 atmospheric pressure in the presence of oxides of vanadium or molybdenum or chromium supported over alumina to get dehydrogenated and cyclized to benzene and its homologues. Homologues means derivatives. That means if we have a 6 carbon containing molecule, we will carry out the aromatization. What are the reagents used for aromatization? We have Cr2O3, V2O5 or MO2O3. We will get benzene. Now if we have toluene, we can prepare it from a 7 carbon containing alkane, and that is going to be heptane. Now let us look at the reaction with steam. If we are reacting it with steam, we will be getting CO plus H2. This is known as water gas. And this water gas can be used for the preparation of dihydrogen gas, which we will study in inorganic chemistry. Moving on to the last reaction, that is pyrolysis. What is pyrolysis? We have a larger alkane which is heated to form smaller homologues, or we can say smaller fragments, and these fragments can either be alkanes or it can be alkenes. Now this is following again free radical mechanism and preparation of oil gas or petrol gas from kerosene oil or petrol, that is involving pyrolysis. So that is the advantage of pyrolysis. For example, dodecane, as we can see over here, this is a bigger alkane that is also undergoing pyrolysis, that is giving a mixed chain of heptane, pentene and other products are also formed in the reaction. So this is all about the theory of alkanes. Now let us do the problems related to alkanes. Let us now do the problems related to alkanes. Question number 1. CH3, CH2, CH3 and CH3C triple bond CH can be distinguished by, if we are using Bayer's reagent or tolerance test or Br2/CCl4, all of these are going to react with the tertiary only and not the primary. So all of these can be used to distinguish these two. So the answer is option number 4. Question number 2, CH3COOK on Kolb's electrolysis. We have to remove this and we have to form the free radical, and we will be getting CH3 single bond CH3. We have to double the number of carbon. Indicate the expected structure of the organic product when ethyl magnesium bromide is treated with heavy water. So this is a reaction of Grignard reagent. If you know about Grignard reagent, let's just do this. Otherwise, just don't get tense, because we have a separate video for Grignard reagent which will be uploaded soon. So we have taken C2H5 MgBr. This is reacting with D2O. So this is going to give us D plus and OH minus or OD minus, and this is going to be the positive side and this is going to be the negative side. The positive side is going to react with the negative side to form C2H5D. So the product is going to be C2H5D. The answer is option number 4. Now here is today's DIY. You have to write down What are the reagents which are used for the following conversions? Comment all the 6 answers in the comment section below. And the top 3 names will be published in the next video. Now let's do another question. A mixture of ethyl iodide and N-propyl iodide is subjected to Wood's reaction. The hydrocarbon that will not be formed is. So we have to find which is not formed. Ethyl iodide contains 2 carbon, so we have to double, that is butane is possible. N-propyl iodide, so we have to double 3, so we get 6, so hexane is also possible. And if we are adding these two, we have 2 carbon here and we have 3 carbon here. Adding, we get 5 carbon, so 5 carbon containing pentane is also present, but propane is not present, so that is going to be the answer for this question. N-hexane on heating in the presence of Cr2O3 will gives benzene because the process is aromatization. So let's move on to the next process. Next question. Hydrocarbon which is liquid at room temperature. We have studied C1 to C4 are gases and C5 to C17 are liquids. So we have pentane as the answer. Which of the following isomers will have the highest boiling point? As we can see, all of these are isomers, and if we have isomers, then we have to consider the long chain. So we are going to consider the first one as the answer. On electrolysis of sodium succinate, the alkene that is obtained is. What is the alkane? We have CH2COONA, CH3COONA, CH3COONA. So we are going to remove this part and we are going to join this with the double bond. So we are getting the ethene over here, and the nature of the solution after electrolysis is going to be basic, which we have already discussed in the theory. Next question. The boiling points and densities of N-pentane, isopentane and neopentane decrease in the order. Highest will be for N-pentane because no branching is present, then comes isopentane and then comes neopentane. So it will be 1 greater than, 2 greater than, 3. So the answer is option number B. Which of the following is the correct sequence of steps in the chain reaction? Initiation, propagation and termination. Answer is option number D. Sodium salt of isobutyric acid on heating with soda lime. Sodium salt of isobutyric acid. So we have CH3, C, CH3. So we have a hydrogen here and we have COONA. So this is going to be eliminated and another same molecule should be added over here. So we have CH, CH3 and we have another CH3. Next question. To carry out the following reactions, we can carry out in the presence of concentrated H3PO4. This is also used. What is X in the following sequence of reactions? X is CH3COOH. Let us take how it is. We have CH4 as the final product. So what will be the corresponding reagent? It will have one more carbon extra, that is CH3COONA. So if we have to subtract Na, we will be getting CH3COOH. We just have to carry out in the reverse order. In chlorination, the relation rate of abstraction of hydrogen in tertiary, secondary and primary carbon are respectively 5:3.8:1. In iodination, for the preparation of iodomethane, the compound used is HiO3 and HgO, so the answer is option number 3. Now this one is again a question which is based on Grignard reagent, we can say. So here also we have, this is the positive sign and this is the negative side. Here we have D plus as the positive side and OD minus as the negative side. So the negative side is going to react with the positive side and the positive is going to react with the negative side. So we have deuterobenzene is the answer. So let us look at this particular question. What is it stating? We have to find what is the compound A. So this is basically decarboxylation. So we have to check by reacting it with NaOH. Every compound, near to every compound, we will write NaOH and we are going to remove an Na2CO3. So we will get the desired product in these two cases. So the answer is option number 4. Name the alkane which cannot be prepared by Wood's reaction, and the alkane which cannot be produced by Wood's reaction is methane. And this is an important question as well. Now let us discuss the next question. Sorry, this is the last question of our discussion. So with this we are ending our first video where we have discussed about alkanes. So in the next part we will be discussing about alkenes and alkynes, that is tomorrow. So stay connected with at NEETshala. You can also join the Telegram channel for all the notes and updates. So stay safe and happy learning.